What if everything around you, everything, the stars, the Earth, you, is just the output of some vast hidden computation? We're about to dive into a radical new theory that claims our universe isn't fundamental at all. Instead, it might just be a simulation running on a kind of cosmic operating system. So yeah, prepare to have your idea of reality turned completely upside down.
So to really get why a theory this wild is even on the table, we've got to start with the single biggest headache in modern physics. For about a century now, our understanding of the universe has been literally split in two, governed by a pair of incredibly successful, yet totally incompatible, rulebooks. See, on the one hand, you got Einstein's universe, general relativity. It gives us this beautiful, smooth, continuous reality, where planets and galaxies follow predictable paths. But then, on the other hand, you have the quantum world. This is the bizarre, pixelated, probabilistic realm of atoms and particles, where things can be in many places at once. One set of rules for the huge, another for the tiny.
And that right there is the question that's kept physicists up at night for generations. Why? Why does reality seem to have two different instruction manuals? Finding one single theory, a theory of everything, that unites them has been the absolute holy grail of physics.
Okay, and this is where our story takes a really interesting turn. A bold new idea has entered the ring, and it's not just a tweak or an update to what we already know. It's a proposal for a complete replacement, a whole new operating system for reality called the Gibsonian framework. The claim here is just breathtakingly ambitious. The idea is to unify all of physics, period. The source material claims that this one computational model can explain everything we see, from starlight bending around the sun to how electrons behave, all with just a simple grid and a few basic rules. So here's the core concept you really have to get. Think about the screen you're looking at right now. The images on it aren't fundamentally real, right? They're just pixels being switched on and off by underlying code. Well, this theory suggests that what we think of as spacetime, matter, and energy are just like that. They're the emergent output of a much deeper, much simpler computational process. Okay, so if the universe is a computer, how does it actually, compute? Let's get into the nuts and bolts. It really comes down to two very simple, fundamental pieces.
First up, you've got the hardware. Forget everything you thought about empty space. In this model, space isn't an empty void. It's made of tiny, discrete points called S-particles, and they're all arranged in this massive 3D grid of tetrahedrons. You can think of them as the pixels of reality. This grid is the fabric of the universe.
And then, of course, you need software. And that comes in the form of these tiny little packets of information called T-particles. Think of them as like digital heartbeats. These little time tokens that are constantly being passed between points on the grid. The entire dynamic universe is just these tokens running the cosmic program.
This is the core process, called the wedge cycle, and it's brilliant in its simplicity. Just imagine there's a tiny clock at every single point in space, but this clock only ticks forward one step in time when it receives a very specific combination of these time tokens, 4 positive ones and 1 negative one. That's it. That one simple, local rule happening everywhere is what supposedly generates all the complexity we see.
Now look, a theory this radical is just a cool story, unless it can actually describe the universe we live in, right? It has to pass the reality check. Does this computational model actually give us the same results we see in the real world?
All right, let's start big. Test number 1. Can this model explain a classic, cornerstone effect of Einstein's theory, like the way a massive object, say our sun, literally bends the path of light that passes by it? So on the left, you've got Einstein's famous formula. It treats gravity as light following a curve in a smooth spacetime. But on the right, you have the Gibsonian way of doing it, where the bending is caused by how the sun's mass changes the flow of those little time tokens on the grid. We're talking two totally different philosophies here.
And here's the part that really makes you go, look at the result. Even with these wildly different mechanics, one continuous, one discrete and computational, the Gibsonian framework's calculation for light bending around the sun comes out to 1.75 arcseconds. It's an exact match with Einstein's prediction and, more importantly, with what we actually observe through our telescopes.
Okay, so it passed a huge cosmic test. But remember, the whole point is to unify physics. So now we have to zoom way in, down to the quantum world, and see if it holds up. Can it describe how an electron behaves inside an atom?
Standard quantum mechanics, as you know, tells us an electron isn't in any one place, it's a probability cloud.
But this new framework says, nope, it's not random at all. It describes the electron's behavior as a deterministic, predictable oscillation based on those token exchanges. And yet, and this is the amazing part, look at the result. It correctly predicts that the electron's most stable spot is the Bohr radius, which is exactly what the standard model tells us.
So it seems to work for the really big stuff and the really small stuff. That's already pretty incredible. But the theory makes an even bigger, even more profound claim, one that really gets to the heart of why our universe is the way it is.
See, our current physics relies on these fundamental constants, basically magic numbers, that we have to go out and measure in experiments. We know what they are, but we have absolutely no idea why they have the values they do. This framework claims it doesn't need to measure them. It can derive them from the pure geometry of its own structure. It's like the rules of the game are baked into the shape of the game board itself.
Take this number. For a physicist, this number is, well, it's about as fundamental as it gets. It's the inverse of what's called the fine structure constant. It's a pure number that basically governs how strong the interaction between light and matter is. It literally dictates how atoms hold together. For decades, we've known the number, but nobody knew why it's that number.
And here is the absolute showstopper claim of the Gibsonian framework. It says this number isn't random at all. It's a direct result of the model's geometry. It's a stable integer, 137, plus this tiny fraction. And that fraction, it's what the author calls a packing tax. It's a little geometric correction factor that just naturally pops out from the math of fitting these tetrahedral pixels into a cubic grid. If this is true, it means one of the deepest mysteries of the cosmos isn't a mystery at all. It's just geometry.
This quote from the author is just perfect. It's a playful reference to Carl Sagan, who famously said that if you want to make an apple pie from scratch, you must first invent the universe. It just perfectly captures the staggering ambition of what's being claimed here. It's not just a model of the universe, it's a proposal for its actual source code.
Now we have to be clear, this is a brand new theory. It has a massive mountain to climb before it's tested, verified, and accepted by the wider scientific community. But it forces us to ask a truly mind-bending question. Are we living in a physical reality, or are we just the emergent phenomena of a few simple rules running on some hidden universal grid? And if our universe really is a computation, who or what wrote the code?